For centuries, Saturn has stood as one of astronomy's greatest paradoxes, a planet so visually delicate that it seems carved from light, yet so physically immense that it could swallow Earth nearly 1,000 times. Its rings, visible through even the simplest telescope, appear serene from afar. But deep within them lies a universe of motion, collisions, resonances, and gravitational choreography, an entire system of particles performing an elaborate dance guided by physics older than the solar system itself. Tonight, we explore Saturn not as a distant gas giant, but as a complex physical structure, one whose rings sing, whose magnetic field whispers, and whose atmosphere archives billions of years of history. This is the silent story of Saturn, and it begins long before the planet formed. Chapter 1: Saturn, the quiet architect of the outer solar system. Among all the planets that inhabit our solar system, Saturn has always occupied a peculiar position, scientifically distant yet visually familiar, enigmatic but unmistakable. No other world has shaped our imagination quite like the sixth planet from the Sunday. For centuries, Saturn has been perceived as a silent giant, a pale yellow sphere wrapped in storms, encircled by rings so broad and delicate they seem more like illusions than matter. But in scientific terms, Saturn is not merely an aesthetic marvel. It is an active laboratory of physics, chemistry, orbital dynamics, and cosmic evolution. And the deeper we investigate this world, the clearer it becomes. Saturn is not silent at all. It speaks in radio waves, in magnetic pulses, and even in the faint vibrations of its rings. To understand Saturn is to confront the complex interplay of forces that define the outer solar system. The planet stands at the boundary between the inner rocky worlds and the massive ice giants farther out. It is a hinge point, a gravitational regulator, and a recorder of ancient events that shaped our cosmic neighborhood. Saturn's orbit, mass, and magnetism influence not only its own satellites but also the architecture of the outer solar system itself. Jupiter may dominate through sheer mass, but Saturn brings structure, stability, and long-term balance. At first glance, Saturn appears deceptively calm, a muted world wrapped in soft bands of beige, ivory, and gold. But beneath the haze lies an atmosphere governed by extreme dynamics. The winds on Saturn can exceed 1,800 kilometers per hour, faster than any storm system on Earth. The planet's upper layers are composed primarily of hydrogen and helium, but deeper down, hydrogen transitions into exotic metallic forms under immense pressure. These layers generate Saturn's unusual magnetic field, which, unlike Earth's neatly aligned dipole, is distorted, drifting, and asymmetrical. In fact, Saturn's magnetic axis is aligned so closely with its rotational axis that scientists spent years struggling to determine the planet's true rotation period. In many ways, Saturn hides its internal clock. Unlike Jupiter, which emits strong, regular bursts of radio waves tied to its rotation, Saturn's magnetosphere behaves more like a flexible membrane. It expands and contracts under the pressure of the solar wind, creating rhythms that mimic but do not directly reflect the motion of the interior. For decades, this confounded researchers. How do you measure the length of a day on a planet whose magnetic field refuses to act like a conventional beacon? The answer came from an unexpected source: the rings themselves. Saturn's rings are not static ornaments. They are vibrating, oscillating, responding to gravitational tides within the planet. In 2013, scientists realized that subtle waves and ripples in the rings matched oscillations deep inside Saturn, like the surface of a drum reacting to tremors within. By analyzing these patterns, researchers derived Saturn's true rotation period, 10 hours, 33 minutes, and 38 seconds. This marked the birth of chronoseismology, the study of Saturn's interior through the seismological behavior of its rings. No other planet in the solar system provides this kind of natural resonant system, a world with built-in sensors orbiting just beyond its surface. But if Saturn's rotation can be detected through the rings, what else might they reveal? Much more, as it turns out. The rings contain clues about ancient collisions, icy fragments, lost moons, and the gravitational history of the Saturnian system. Their composition, water ice with trace impurities, suggests they are relatively young, perhaps no more than 100 million years old. In cosmic terms, that means the rings were not present during the time of the dinosaurs on Earth. They are a recent addition, bright and reflective because they have not yet been darkened by dust. The rings do more than reflect sunlight and sculpt patterns. They interact with Saturn's magnetic field, generating electromagnetic signals that can be measured by passing spacecraft. NASA's Cassini mission discovered that tiny grains of ice continually leak from the rings into Saturn's upper atmosphere, forming a kind of ring rain. These particles carry electric charge and alter the composition of the ionosphere, subtly shaping the planet's chemistry. In other words, Saturn's rings are not passive, they are participants in a feedback system between planet, magnetosphere, and space environment. At the same time, Saturn's magnetic field is unusually quiet compared to Jupiter's explosive radio emissions. Saturn's magnetosphere hums at lower frequencies, producing periodic pulses shaped by the solar wind. These signals converted to audio resemble distant choral tones or slow, drifting waves. They are sometimes called Saturn song. They are not literal music, but they are real physical vibrations, radio emissions generated by energetic charged particles spiraling along magnetic field lines. And they change with the seasons, with the solar cycle, and with the influx of material from the rings and moons. Among Saturn's many moons, Titan stands out as a world that could have been its own chapter in planetary evolution. Enceladus, meanwhile, brings complexity to a new level by venting plumes of water vapor, organics, and salts into space. These plumes not only feed Saturn's E-ring but also introduce new particles into the magnetosphere, affecting its dynamics in ways that scientists are still working to understand. Saturn's system, therefore, operates as a connected ecosystem, rings influencing the magnetosphere shaping atmospheric chemistry, moons feeding plasma, and solar wind modulating the entire configuration. Taken as a whole, Saturn is not a quiet planet. It is an orchestrated structure of moving gases, rotating fields, interacting particles, and resonant rings. Its silence is only apparent. It is, in fact, a world broadcasting continuous scientific signals. The challenge is not hearing them, but interpreting them. This chapter lays the foundation for understanding Saturn not as a decorative figure in the solar system, but as a dynamic world whose rings are instruments of inquiry, whose atmosphere is a laboratory of physics, and whose magnetic field is a channel for energy and information. In the chapters that follow, we will examine how the rings form and evolve, why they sing, how the magnetosphere stores and releases energy, and what Saturn can tell us about the early solar system and the behavior of planets beyond our own. Chapter 2: The Architecture of a Ringed World. Saturn is often described as the most visually striking planet in the solar system. and while its rings dominate every artistic rendering, the planet beneath them is equally extraordinary. To understand why the rings behave the way they do, why they oscillate, fragment, twist, and sing, we first need to examine the physical structure of Saturn itself. Saturn is not simply a gas giant, it is a vast, multi-layered sphere of hydrogen-dominated fluid dynamics. Rapid rotation, deep atmospheric convection, and a magnetic field strong enough to sculpt the space around it. Every layer, from its translucent upper haze to its metallic hydrogen core, contributes to the gravitational and electromagnetic environment that the rings inhabit. Saturn is the second largest planet in our cosmic neighborhood, with a diameter roughly 9 times that of Earth. Yet its mass, though immense, is surprisingly low for its size. It is the least dense planet in the solar system, so light, in fact, that if one could drop it into a hypothetical ocean wide enough, Saturn would float. This low density is not just a curious fact, it is a defining feature of the planet's internal physics. Saturn is composed almost entirely of hydrogen and helium, gases that are compressed into exotic phases under extreme pressure. What looks serene from a distance is, in reality, a colossal fluid sphere where matter behaves differently than anything found naturally on Earth. The outermost layer of Saturn is a tenuous and complex atmosphere composed primarily of molecular hydrogen, H2, helium, He, trace hydrocarbons, and ammonia ice. Its familiar pale yellow and cream bands arise from ammonia crystals and photochemical reactions triggered by sunlight. But beneath this cloud deck lies a zone of intense storms and convective currents. Saturn's equatorial winds can reach speeds of over 1,800 kilometers per hour, stronger than any jet stream or hurricane on Earth. These winds are not driven by sunlight, but by the planet's internal heat. Saturn radiates more than twice as much energy as it receives from the Sun, a reminder that the world remains geologically and thermally active despite being over 1 billion kilometers away from its energy source. As we pass deeper, pressure rises to millions of Earth atmospheres. Hydrogen transitions from its familiar molecular form to a dense, electrically conductive metallic phase. Metallic hydrogen is unlike any material available on Earth without extreme laboratory systems. It behaves as both a liquid and a conductor, allowing convection currents to generate Saturn's magnetic field via dynamo action. The magnetic field that emerges is surprisingly symmetrical, more axis-aligned than Jupiter's, and this symmetry plays a subtle but important role in how charged particles move around Saturn and interact with the rings. Saturn's magnetic environment influences everything from auroras at the poles to the dust and ice distribution within the rings. Charged grains in the rings can become temporarily trapped in pockets of electromagnetic turbulence. Minute electrostatic interactions, invisible to the naked eye, can shift or tilt entire ringlets, creating the ripples and undulations detected by the Cassini spacecraft. The rings are not merely passive debris orbiting Saturn. They are interacting constantly with a dynamic magnetosphere shaped by the planet's metallic heart. The deeper layers of Saturn reveal even more complexity. Beneath the metallic hydrogen region may lie a core composed of rock, ices, and heavier elements, an object perhaps 10 times the mass of Earth. For decades, astronomers debated whether such a core existed at all. However, studies from Cassini's grand finale orbits, which measured subtle variations in Saturn's gravitational field, suggest that the core is not a solid, compact sphere, but a fuzzy or dilute core. This means that the boundary between metallic hydrogen and the deeper materials is blurred, with heavy elements gradually mixing outward into the planet's envelope. In effect, Saturn has a core that is partially dissolved, spread across a significant fraction of its radius. This fuzzy structure carries profound implications for the rings. Precise gravitational measurements indicate that oscillations deep within Saturn, planetary scale waves in its interior propagate outward and imprint themselves on the rings. These waves subtly modulate the orbital paths of ring particles, carving gravitational fingerprints into the ice. From these disturbances, scientists have performed a form of planetary seismology, reading Saturn's interior by studying vibrations recorded in the rings. The rings become a natural seismograph, detecting oscillations far beneath Saturn's clouds. In this sense, Saturn is not silent at all. Its internal modes resonate outward, disturbing the rings in patterns that can be mathematically decoded. This interaction between the planet's interior and its rings is one of the most remarkable scientific discoveries of the Cassini mission. It reveals a connection more intimate than was ever imagined. Saturn influences its rings not only through gravity but through the physical symphony of its internal structure. The rings respond to the oscillations the same way sand on a vibrating plate arranges itself into geometric patterns. Although these variations are far too subtle for human eyes, sophisticated instruments detect them with precision. The atmospheric dynamics of Saturn also play a role in shaping the environment of the rings. The planet's rapid rotation, one full spin every 10.7 hours, creates an oblate shape with the equator bulging outward. This slight equatorial flattening affects the gravitational field experienced by ring particles, stabilizing the broad, flat geometry of the rings. The rings lie in Saturn's equatorial plane because the forces created by its shape effectively anchor them there. The planet's rotation is not just a surface characteristic, it is a structural element that defines the ring system's stability. Saturn's weather also produces immense storms capable of altering the planet's thermal balance, which, in turn, influences the behavior of the magnetosphere. Approximately every 30 years, Saturn unleashes a great white spot, a planetary-scale storm system that wraps around the entire globe and persists for months. These storms inject heat and chemical anomalies into the upper atmosphere, which modulate how the planet radiates energy. Although the direct impact on the rings is subtle, long-term shifts in thermal emission eventually influence the distribution of charged particles, affecting the electrostatic environment in which ring grains exist. Meanwhile, the planet's auroras, driven by solar wind and internal magnetospheric currents, illuminate the poles with far ultraviolet light invisible to human vision. These auroras arise through interactions of charged particles with atmospheric gases, the same processes that shape Earth's northern and southern lights. But on Saturn, the auroral oval is influenced by interactions with its moons, especially Enceladus, which vents water vapor and charged particles from its south pole. These particles eventually join Saturn's magnetosphere and create a plasma environment that interacts with the rings, subtly modifying their composition and structure over time. Thus, Chapter 2 reveals Saturn not as a passive backdrop to its iconic rings, but as a dynamic, layered, constantly evolving world. Its atmosphere churns with storms far larger than continents. Its magnetic field is born from metallic hydrogen currents deep beneath the surface. Its gravity pulses with internal oscillations that reach outward to inscribe patterns into the rings. Every scale from the core to the cloud tops from the magnetosphere to the faintest ring particle, interacts through energy, motion, and resonance. Saturn is a system of systems, a planet and its rings, inseparable in behavior, though distinct in form. Understanding Saturn's internal architecture is the first step toward understanding why its rings behave like an instrument responding, vibrating, and singing in patterns that carry the secrets of a world made not of rock, but of motion. Chapter 3: The Architecture of Saturn's Rings. Order inside chaos. As we move beyond the origin of Saturn's rings and the fragile balance of forces shaping them, a deeper question naturally emerges. How are these countless particles organized into structures so precise they rival engineered systems? From a distance, Saturn's rings appear smooth like a single sheet of reflective ice stretched around a gas giant. Yet up close, spacecraft observations reveal that they are anything but uniform. They are divided, stratified, braided, warped, and sculpted by invisible forces, acting across hundreds of thousands of kilometers. To understand Saturn, one must step inside the architecture of its rings, an immense, dynamic structure where physics operates with a clarity rarely seen elsewhere in the solar system. The rings are not only a collection of particles, they are a living demonstration of orbital mechanics, resonances, and gravitational choreography. 1. A system of layers, the main divisions of the rings. Saturn's rings are traditionally divided into several major components: D, C, B, A, F, G, and E rings, arranged from the planet outward. Each ring is physically distinct, with its own density, thickness, albedo, and dynamical behavior. The B ring, the titan of the system. The B ring is the largest and most massive segment, making up nearly half the total mass of the ring system. Its brightness suggests high reflectivity, and its density waves, spiral structures, and gravitational wakes reveal a system far more dynamic than a simple disk. Estimates suggest that regions of the B ring may reach optical depths of more than 5, meaning radiation barely penetrates its densest segments. The Cassini division, not empty, but sculpted. Between the A and B rings lies the Cassini division, a vast 4,800-kilometer wide gap, created not by absence, but by gravitational resonance. More specifically, the 2-to-1 orbital resonance with Saturn's moon, Mimas. For every orbit a particle completes here, Mimas completes exactly half, creating periodic tugs that eject particles from the region. This is not a gap carved by collision, but a gap carved by mathematics. The A ring, a realm of resonances. The A ring, though less massive than the B ring, is a laboratory for wave patterns. Here, spiral density waves curl across its width, driven by the gravitational influence of multiple moons. These wave structures travel much like ripples on a pond, except the pond is composed of ice fragments orbiting at tens of thousands of kilometers per hour. 2. Gravitational sculptors, moons that shape the rings. Saturn's ring system cannot be understood without acknowledging the roles of its moons, shepherds, sculptors, and disruptors. These small bodies exert gravitational influence that shapes the rings into intricate patterns. The shepherd moons of the F ring. Prometheus and Pandora orbit on either side of the thin, erratic F ring. Their gravitational pulls act like hands stretching and compressing a silk ribbon. Prometheus steals material from the ring, creating streamers. Pandora tugs from the opposite side, pulling the ring outward. The result is a ring that twists, braids, clumps, and reforms constantly. Pan and Daphnis moons within the rings. Pan and Daphnis, two moonlets embedded within the A ring, carve narrow gaps known as the Encke and Keeler gaps. As they orbit, they create waves on the edges of these gaps: vertical waves, radial waves, and spiral waves, just as a ship creates wakes on water. This phenomenon demonstrates an essential principle of orbital dynamics. A moon embedded in a disk cannot move without the disk responding. Mimas, the global sculptor, while small shepherd moons shape local structures, Mimas governs macro-scale features like the Cassini division. Its orbital resonance is powerful enough to reorganize entire ring regions, clearing particles and maintaining large-scale boundaries. 3. Waves that travel through ice. The physics of density and bending waves. Saturn's rings are not static. They behave like a vibrating sheet composed of trillions of particles. Density waves. Triggered by gravitational resonances with nearby moons, density waves propagate outward as spiral ripples. These waves compress particles into alternating high-density and low-density regions, forming tightly spaced bands. Their behavior is mathematically identical to the way galactic spiral arms form. Another example of Saturn acting as a microcosm of cosmic phenomena. Bending waves. When a moon's orbital plane tilts relative to the rings, its gravitational influence produces vertical oscillations, tiny vibrations that make the rings warp. These bending waves give certain ring zones a corrugated appearance, like ripples on a metal sheet. Self-gravity wakes. In dense regions, especially the B ring, particles clump temporarily due to mutual gravity, forming elongated structures tens of meters across. These clumps rapidly form and break, producing a striped appearance in high-resolution images. This is the ring system's attempt to organize itself under its own self-gravity. 4. How thick are the rings and why it matters? For a structure spanning 280,000 kilometers in diameter, the rings are astonishingly thin, only about 10 meters thick on average. This means the ratio of width to thickness is comparable to a sheet of paper stretched across a football field. Why so thin? Because collisions continually redistribute vertical motion into horizontal motion. If a particle strays upward, it collides, loses vertical energy, and returns to the plane. Over millions of years, this mechanism forces the ring into an ultra-flat configuration. The thinness of the rings is a direct signature of collisional evolution, a process that stabilizes the disk and reveals its age and dynamical history. 5. Microstructures, propellers, spokes, and transient phenomena. Beyond the grand structures are smaller, transient features that hint at unseen processes. Propeller structures. In the ring, moonlets too small to clear full gaps still disturb their surroundings, creating propellers, shaped disturbances that rotate with the moonlets. These structures indicate the presence of bodies only tens to hundreds of meters wide, invisible in direct images. Radial spokes. First observed by Voyager, spokes are dark, radial streaks that appear and disappear within hours. Scientists believe they are electrostatic phenomena, particles levitated above the ring plane by Saturn's magnetic field. Ballistic transport. Impacts on the rings eject icy material that can travel long distances and settle elsewhere, slowly redistributing brightness across the ring system. Each of these microstructures hints at Saturn's complexity. The rings are not merely a passive disk, they respond actively to impacts, electrostatic forces, and internal particle collisions. 6. The rings as a system in balance. The architecture of Saturn's rings is governed by a delicate equilibrium between gravity, orbital resonances, collisions, electromagnetic forces, tidal interactions, the influence of dozens of moons. Every feature from gaps to waves to braids is a visible trace of invisible forces. Saturn's rings are often compared to laboratory plasma disks, galaxy disks, and planetary accretion disks. Their physics is universal. Local interactions produce global structure. In many ways, Saturn's rings are the most accessible example of how order emerges from chaos through natural laws. As we've explored the architecture etched into Saturn's rings by gravity and orbital mechanics, a natural next question arises. What happens when these forces clash, overload, or fall out of balance? In the next chapter, we examine the darker, more energetic side of Saturn's ring system, the collisions, disruptions, and violent processes that continually reshape the disk over geological time. Chapter 4: The Origin of the Rings, a System Built from Violence. The Illusion of Permanence. When we look at Saturn through a telescope, the rings seem ancient, serene, and immutable, like a cosmic monument that has existed since the dawn of the solar system. For centuries, scientists believed exactly that. The rings were thought to be primordial, forming alongside Saturn itself 4.5 billion years ago. But modern research tells a very different story. Spacecraft data from Voyager, Cassini, and Earth-based spectrometry show that Saturn's rings are shockingly young, perhaps no more than 10 to 100 million years old. In cosmic terms, this is recent enough that the dinosaurs might have seen Saturn without its rings if they'd had telescopes. The rings appear bright because they are composed of remarkably clean water ice, almost untouched by the micrometeoroid dust that darkens ancient surfaces. Something has been continually resurfacing or replenishing them, or they were created recently enough that they simply haven't aged. This is where the illusion of permanence breaks. The rings are beautiful precisely because they are fragile and transient, not timeless. To understand them, we must understand the event that created them. 2. The forensics of a planetary crime scene. Imagine a forensic scientist arriving at a scene and reconstructing the sequence of events from subtle traces left behind. Planetary scientists do something very similar when they study Saturn's rings. They analyze particle size distribution, ice purity, orbital resonance patterns for debris motion, gravitational boundary conditions, and the conclusion is consistent. Saturn's rings were formed from something that was violently torn apart. The question is, what was destroyed? There are two major hypotheses, both supported by strong evidence, and each offers a different tale of catastrophe. Hypothesis 1: the lost moon theory. Perhaps the most widely accepted explanation is that Saturn once possessed a moon similar in size to Enceladus or Mimas that ventured too close to the planet. This moon, orbiting gradually inward due to tidal interactions, eventually crossed the Roche limit. The Roche limit is a gravitational boundary discovered by Edouard Roche in 1848. Inside this region, tidal forces become so strong that a large celestial body held together only by its own gravity cannot remain intact. Saturn's Roche limit lies roughly 2.4 Saturn radii from its center, close to where the densest rings exist today. Inside this boundary, the tidal forces are overwhelming. They pull harder on the near side of the moon than the far side. The difference in gravitational acceleration becomes extreme enough to shatter rock and ice. If a moon enters this region, Fractures form. The moon elongates. Surface material peels away. Large chunks shear off. Eventually, the entire body disintegrates. Cassini's data on the composition of the rings composed of 99% pure water ice implies this moon's outer layers were dominated by ice, making it vulnerable to disintegration. The rings we see today may be the remnants of that world, a former moon pulled apart into trillions of fragments, each now circling Saturn as a frozen echo. IV. Hypothesis 2. The aftermath of a cosmic collision. A second hypothesis proposes a different form of destruction. Instead of tidal disassembly, the rings could be the result of a giant collision between two of Saturn's moons. The outer solar system is not as calm as it seems. Moons can be perturbed by gravitational resonances, chaotic orbital evolution, passing cometary bodies, interactions with Titan's immense gravity. If two medium-sized moons were nudged into intersecting orbits, a collision could occur at velocities of several kilometers per second, enough kinetic energy to pulverize ice and rock into a cloud of debris. Computer simulations show that such a collision would naturally produce small, icy fragments that spread into rings, rocky cores that may reaccrete into new moons, spiraling debris that gradually organizes into narrow bands. This model explains why the rings contain so little rock. The lighter, icy material spreads outward and forms rings, while denser rocky remnants might merge into new moons, possibly explaining bodies like Mimas, whose internal structure suggests incomplete reaccretion. In this scenario, the rings are the residue of a lost family of moons, a system reshaped by catastrophic impact. V. Why the ice is so pure. Regardless of which origin scenario is correct, the ring's high ice purity requires special explanation. Pure water ice is highly reflective. Over millions of years, however, continuous bombardment by micrometeoroids should darken the rings significantly. The fact that they remain bright suggests they are young, possibly less than 100 million years old, or they undergo a self-cleaning process through collisions that expose fresh surfaces, or material from Enceladus's geysers replenishes the rings. Cassini measured in falling dust rates into Saturn's atmosphere and into the rings themselves, revealing that the rings will eventually darken and disperse. This means the current state of the rings is temporary. They are not only young, they are mortal. V. A structure sculpted by gravity. Once formed, the rings did not remain as a chaotic debris field. Saturn's moons rapidly began sculpting them through gravitational interactions. The result is the delicate structure seen today. Gaps carved by moon resonances, waves driven by orbital forcing, spiral density patterns, shepherd moons corralling material. Within a few thousand years, an instant in planetary timescales, the disordered debris settled into the ordered system we recognize now. Thus, the rings are not simply a relic of destruction, they are the product of reorganization, shaped by gravity into coherent form. 7. The timeline of a cosmic event. Pulling together all lines of evidence, scientists can reconstruct a plausible timeline. 1. A moon approached the Roche limit or collided with another moon. 2. The moon fractured, shedding material into orbit. 3. Debris spread around Saturn over tens of thousands of years. 4. Gravitational resonance shaped the debris into discrete rings. 5. Shepherd moons formed or reformed, tightening the structure. 6. Micrometeoroid bombardment and collisions refined the particle sizes. 7. The rings achieved their modern appearance sometime within the last 100 million years. This is a story of creation born from loss, a reminder that beauty in the cosmos often emerges from violence. 8. The rings as a moment in time. Saturn's rings are neither permanent nor primordial. They are the result of a temporary cosmic circumstance, and future generations may see a Saturn with faint or invisible rings as they gradually decay and fall into the planet. What we see today is a snapshot, a brief, luminous chapter in Saturn's long history. And as we close this chapter, another question naturally emerges. If Saturn's rings were born from destruction, how do they influence the present-day system of moons and gravity surrounding the planet? Chapter 5: The Engine of the Rings. Why Saturn's ring system never stops evolving. Saturn's rings, despite their serene appearance, are not static structures. They are dynamic, restless, and continuously sculpted by an intricate network of forces: gravitational, electromagnetic, collisional, and thermal. In this chapter, we move beneath the visual elegance of the rings and into the mechanical and physical engine that drives their evolution. Much of what we know today comes from spacecraft flybys, particularly NASA's Cassini mission, which spent 13 years orbiting Saturn and revealed the rings as a laboratory of celestial mechanics in constant motion. 1. A world made of billions of particles. Saturn's rings are not solid sheets, but rather collections of individual particles, ice fragments ranging from microns to boulders nearly 10 meters wide. Each particle orbits Saturn independently, governed by the same laws of motion that control planets and moons. When seen up close, the rings behave more like rivers of orbiting debris than like the flat disks we imagine from telescopic images. These particles collide, scatter, accrete, and drift. A single meter-sized block might collide thousands of times per year because the rings are dense. In the brightest regions, a cubic meter of space is enough to encounter dozens of ice grains. Every collision transfers momentum, heat, and angular energy. This makes the rings behave as a giant granular fluid. Their patterns, waves, splits, braids, and spokes are not static drawings but visible expressions of fluid dynamics on a planetary scale. 2. Differential rotation, the source of ring structure. Because inner particles orbit Saturn faster than outer ones, the rings experience what astronomers call Keplerian shear. This difference in rotation is the origin of many ring features: waves that stretch into long spirals, gaps that are constantly sharpened, edges that behave like vibrating strings, sheared clumps that elongate and disperse. The B ring, for example, contains waves created by gravitational resonances with Saturn's moons. These waves can be hundreds of kilometers long, but only a few meters tall, gentle distortions in the orbital plane that propagate like ripples in a frozen river. To Cassini's radar instruments, they appeared as fine corrugations, like the grooves on a vinyl record. Differential rotation is also responsible for preventing large bodies from forming. Gravity wants to gather particles, shear tears them back apart. It is a constant competition between order and dissolution. 3. Resonances, the invisible hands shaping the rings. Earlier, we examined how moons influence ring edges. Here, we go deeper into the physics. Orbital resonances occur whenever ring particles orbit Saturn in exact numerical ratios, with a moon's orbital period 2:1, 3 to 2, 5 to 3, and so on. At each resonance point, the Moon applies a periodic gravitational nudge. One nudge is weak, thousands, perfectly timed, create structure. These resonances produce spiral density, waves compression, and rarefaction of particles, bending waves, vertical oscillations above and below the ring plane, sharp gaps such as the Anchor and Keeler gaps, wave trains that travel across the rings like concentric ripples. Resonances are the reason the rings contain 10,000 plus observable features, an entire symphony of gravitational forcing, with each moon playing its own rhythmic role. One of the most striking examples is the Mimas 2:1 resonance, which clears the entire Cassini division. Even though Mimas is relatively small, its persistent gravitational pull creates a gap 4,800 kilometers wide. It is a vivid demonstration of how orbital mechanics shapes entire landscapes. 4. Collisional physics, the micro-engine of ring evolution. At the smallest scale, Saturn's rings are governed by collision physics. When ice particles collide, they don't shatter violently. Their surfaces are so cold that impacts are often soft, plastic, and energy absorbing. These collisions dampen vertical motion, redistribute angular momentum, cause particles to settle into a thin plane, create clumps and temporary aggregates. Cassini observed propellers disturbances created by unseen kilometer-scale bodies embedded in the rings. These objects are too small to form moons but too large to behave like simple particles. They carve shaped trails and act like geological features drifting through the ring landscape. Propellers are evidence that Saturn's rings contain an entire population of moonlets, each altering the dynamics around it. The rings, therefore, are not only shaped by moons, they are shaped by objects trying to become moons, but never fully succeeding. 5. Electromagnetic forces, the subtle sculptors. Not all particles respond only to gravity. The smallest grains, micron-sized ice dust, become electrically charged by solar radiation, plasma interactions, UV photons, collisions. Because Saturn sits in a magnetosphere, these charged grains respond to electromagnetic forces. This creates features that gravity alone cannot explain, such as the famous spokes of the B-ring. Spokes are temporary, ghost-like radial streaks that appear and vanish over hours. They rise above the ring plane like dust suspended in an electric field. Cassini discovered that the spokes correlate with Saturn's magnetic rotation, meaning they are synchronized with the planet's internal magnetic field rather than with orbital motion. This is why the rings seem to speak electromagnetically. They respond to Saturn's magnetic heartbeat. 6. Meteoroid bombardment, the aging process. Although the rings appear pristine, they are constantly bombarded by micrometeoroids, tiny fragments traveling at tens of kilometers per second. Each impact ejects dark material, contaminating the ice and slowly turning bright regions more opaque. This is one of the strongest clues that Saturn's rings are young, perhaps only 100 million years old. If they had existed since the formation of the solar system, they would be much darker. The rings are being gradually eroded. Their brightness is a temporary chapter in their long story. Meteor bombardment also injects heat and ejecta into the ring plane, altering local densities and planting chaotic signatures throughout the system. Every impact, even microscopic, echoes across thousands of particles. 7. Ring rain, the slow fall towards Saturn. One of Cassini's most surprising discoveries is that Saturn's rings are slowly disappearing. Electrically charged dust and water molecules spiral inward along magnetic field lines, falling into Saturn's upper atmosphere. This phenomenon, called ring rain, removes up to 10 tons of material per second. Ring rain affects Saturn's atmospheric chemistry, injecting water, oxygen, and other volatiles into the equatorial regions. Saturn's atmosphere literally contains the dissolved remnants of its rings. This process hints that the rings are transient structures, complex, beautiful, but temporary. They may vanish in 100–300 million years, leaving only faint residual debris. 8. A system in motion, not in stasis. Viewed through a scientific lens, Saturn's rings are not monuments. They are machines, complex, active, and self-modifying. Every moon, every grain, every wave is part of a multi-scale system. Large-scale, gravitational sculpting by moons. Mid-scale, collisional dynamics and wave propagation. Micro-scale, electromagnetic charging and dust transporting. The rings are constantly rewriting their own structure. They contain memory patterns that reflect events thousands of years old, and they also erase themselves. This continual evolution is why scientists treat the ring system as a natural laboratory for understanding the behavior of disks across the universe, from planetary rings to protoplanetary disks around newborn stars. Chapter 6. The rings as a living archive of the solar system. The rings as stratified time layers. Saturn's rings appear from a distance, like a single halo of light. But when observed through the eyes of Cassini, they reveal themselves as a complex, multi-layered system of fine structures, braided strands, density waves, bending waves, gaps carved by moons, and spirals etched by resonance. Each of these structures corresponds to a moment in time, a passing comet that was torn apart, a moonlet that drifted too close to the Roche limit, a gravitational oscillation inside Saturn's core, a collision between particles hundreds of meters wide, a brief surge in meteoroid impacts. The rings are not static architecture, they behave like sedimentary layers in geology. Except instead of rock, they store time in ice, in orbits, and in patterns of motion. Every ripple is a timestamp. Every wave is a record of an event. Every gap is a scar. When Cassini scanned these patterns, planetary scientists quickly realized something unprecedented. Saturn's rings are the most detailed historical archive of gravitational behavior in the entire solar system. No seabed, no glacier, no asteroid surface holds more information about the forces that shaped it. Density waves. The rings respond to moons. A density wave begins when one of Saturn's moons, orbiting outside the rings, exerts a periodic gravitational tug on ring particles. This tug compresses particles into tightly packed regions, creating long spiral bands that wind outward like ripples from a stone dropped into a pond. Unlike waves in water, these spirals do not fade quickly. They can persist for centuries. Every moon creates its own unique pattern, an orbital signature. Mimas produces the prominent 2:1 resonance gap in the B ring. Janus and Epimetheus produce subtle overlapping patterns. Enceladus, with its complex tidal rhythm, imprints faint modulations across the ring. These waves reveal not only the positions of moons but also their mass, their orbital drift, their internal structure, and the rate at which they exchange angular momentum with the rings. No telescope on Earth can measure such precise lunar details. The rings do it for us. 3. Bending waves. Saturn's rings are not flat. Although Saturn's rings appear to be razor-thin, high-resolution imaging revealed that portions of them warp vertically, tilting up and down like sheets of paper disturbed by a passing breeze. These oscillations, known as bending waves, are triggered by moons whose orbits are slightly inclined relative to the ring plane. Each wave lifts ring particles several hundred meters above the nominal plane and then lets them fall again. These waves encode information about the vertical thickness of the rings, the speed at which particles collide and settle, and the gravitational influence of Saturn's tilted moons. Because these waves propagate vertically, they serve as 3D seismographs, mapping how the ring plane flexes through space. IV. Meteoroid bombardment. The rings record impacts like fresh snow. Every year, thousands of micrometeoroids strike Saturn's rings. Some embed themselves into ice particles, darkening them. Others blast out radial scars that spread over time. For most celestial surfaces, such as the Moon or Mars, impacts accumulate for billions of years, erasing older signs. But Saturn's rings are different. Their particles are constantly colliding, exchanging material, drifting, and redistributing mass. This behavior refreshes the surface much like wind smoothing out sand dunes. Therefore, the ratio of bright to dark ice indicates how long the rings have been exposed to space. Cassini's cosmic dust analyzer measured these impurities, leading to an astonishing conclusion. Saturn's rings are geologically young, perhaps no older than 100 million years. In solar system terms, they are practically newborn. This youthfulness makes them even more valuable as archives. Their records are detailed, clean, and unburied by deep time. V. Embedded moonlets, hidden sculptors in the ice. Although Saturn possesses more than 140 known moons, it also contains dozens of moonlets embedded within the ring's objects, too small to be considered full moons, but large enough to sculpt ring material around them. These moonlets create propeller-shaped gaps, local density clusters, small shock waves, and asymmetric disturbances. One moonlet, named Daphnis, produces vertical waves that rise up like walls as it glides through the Keeler Gap. Another, Pan, sculpts the Anchor Gap with spiraling patterns. By studying these distortions, scientists deduce the internal density of moonlets, how they accrete or shed material, and how ring systems evolve into moons over time. In essence, the rings are not only archives, they are laboratories of moon formation. The resonances as planetary seismographs. Some of the most delicate waves in the rings are caused not by moons but by Saturn itself. Saturn oscillates its interior, vibrates through gravitational modes, much like a star. These vibrations slightly alter Saturn's gravitational field, which travels outward and interacts with ring particles. The rings respond by forming chronoseismology waves, subtle ripples whose wavelengths encode the density of Saturn's core, the presence of layered shells of metallic hydrogen, the rotation rate of the planet's deep interior. Before Cassini, Saturn's internal rotation was one of the great unsolved problems of planetary science. But the rings acted as a natural seismograph, a planetary body using its rings to broadcast information about its own interior. This is one of the most profound scientific revelations of the Cassini era. The rings as an evolutionary story. Saturn's rings record four intertwined histories. 1. The history of Saturn's moons, how they migrate, interact, form, and sometimes get destroyed. 2. The history of Saturn's interior. Vibrations deep inside the planet create visible ripples far above. 3. The history of the solar system's debris. Impacts, comets, and fragments leave scars in the icy bands. 4. The history of gravity itself, how resonances, tides, and orbital mechanics shape matter on massive scales. The rings are vast enough, intricate enough, and dynamic enough to preserve events across many timescales, from minutes to millions of years. No other celestial structure provides such a readable record. 8. A living archive that will someday disappear. However, this archive will not last forever. Cassini discovered that Saturn's gravity pulls ring particles inward. Charged particles drag ice grains along magnetic field lines, and meteoroid darkening accelerates decay. The rings are raining onto Saturn slowly, steadily, inevitably. In perhaps 100 million years, the archive will be gone. It is a reminder that even the most stunning features in the solar system are temporary, existing only for a moment on cosmic timescales. But while they exist, they offer clarity into the mechanisms of planetary evolution that no other structure can match. Chapter 7. The Architecture of Saturn's Magnetosphere. 1. The Scale of a Magnetic Giant. Saturn possesses the second largest magnetosphere in the solar system, surpassed only by Jupiter's, yet its nature is distinctly different. Where Jupiter's magnetic field is turbulent, aggressive, and reactive, Saturn's is smoother, more symmetric, and unusually aligned with its rotation axis. Saturn's magnetic dipole is tilted by less than 1 degree relative to its spin. No other planet in our system displays such near-perfect alignment. In practical terms, this symmetry produces a magnetosphere that behaves almost like a massive, synchronized resonator, a chamber where fields, plasma waves, and charged particles organize into elegant patterns. The size of this structure is staggering. On the day side, the side facing the Sun, the magnetosphere is compressed by the solar wind into a boundary roughly 20 Saturn radii from the planet. But on the night side, the magnetotail stretches outward for millions of kilometers, forming a plasma corridor that spirals behind Saturn as it orbits. In this vastness, energy moves slowly. Waves propagate like deep ocean swells. Charged particles drift in methodical patterns. It is here that Saturn's rings interact with and occasionally influence the magnetic field, a rare phenomenon among planets. 2. A magnetosphere fed from within. Unlike Earth, Saturn's magnetosphere is not dominated by particles from the solar wind. Instead, it is internally sourced, and the primary contributor is one of the most remarkable worlds in the solar system, Enceladus. The icy moon ejects water vapor, ice grains, and organic compounds from its south pole fissures. These plumes form a torus, a donut-shaped cloud around Saturn. Within this torus, water molecules are ionized, producing H2O-, O-, OH-, and a mixture of charged particles that spread into Saturn's magnetosphere. This internal plasma supply does more than fill the magnetosphere. It slows the rotation of the magnetic field itself through a process known as mass loading. As new ions are injected into the system, Saturn's magnetic field must carry them along, redistributing angular momentum and forming currents that flow between the planet and its rings. This connection, Saturn to Enceladus to the rings, is one of the most interconnected electromagnetic environments found anywhere in the solar system. 3. The ring magnetosphere coupling. If Saturn's rings were merely passive structures made of ice, their relationship with the planet's magnetic field would be unremarkable, but the rings are electrically active. The constant bombardment of ultraviolet light from the sun charges the ice grains, producing an environment dense with electrostatic interactions. Because of this, the rings act almost like a vast, two-dimensional plasma surface. Charged particles from Saturn's magnetosphere interact with the rings in several ways: electrostatic binding and repulsion between grains, magnetic torque that subtly shapes ring dynamics, deposition of charged particles onto ring surfaces, removal of ring material as ions sputter ice grains apart. The rings also respond to changes in Saturn's magnetic field. During Cassini's grand finale, when the spacecraft flew between the innermost ring and the planet itself, it detected significant electromagnetic activity generated by ring particles. In a very real sense, the rings sing because they are electrically alive, resonating with field lines that sweep through them like waves across a harp. 4. Field lines that carry soundless music. Saturn's magnetic field lines oscillate. These oscillations, known as magnetohydrodynamic MHD waves, propagate through the magnetosphere like vibrations through a giant tuning fork. Cassini recorded these oscillations in the form of radio emissions, specifically a class of signals called Saturn kilometric radiation, SKR. SKR is produced when energetic electrons spiral along magnetic field lines and collide with Saturn's ionosphere. The resulting emissions vary in intensity, shape, and frequency depending on solar wind pressure, dust density within the ring zone, plasma output from Enceladus, rotational modulation of the magnetic field. SKR is not sound in the traditional sense, but when converted into audio frequencies, it becomes eerily melodic, rising tones, pulsing crescendos, and whisper-like fluctuations that resemble a cosmic duet between Saturn and the Sunday. These emissions are part of what some scientists refer to as the singing magnetosphere. They form an essential part of Saturn's silent story waves that reveal the structure and behavior of the magnetic environment, even when invisible to human eyes. 5. Auroras on a clockwork planet. Saturn's auroras are unlike those on Earth. Because of the near-perfect alignment of its magnetic field, the auroras form remarkably circular ovals around the poles, steady, symmetric, and often dominated by ultraviolet light. These auroras respond to two main drivers: solar wind compression, which brightens and intensifies the polar regions, internal plasma injection, primarily from Enceladus. Cassini observed auroral storms that were linked to large-scale reconfigurations of Saturn's magnetic field. When the magnetosphere becomes overfilled with ions, excess plasma is expelled down the magnetotail in a dramatic process called plasmoid ejection. These events release enormous bursts of magnetic energy, causing auroras to brighten and expand. Saturn's auroras are therefore not only indicators of solar wind conditions, they are windows into the internal plasma dynamics of the entire system. 6. Rotational mysteries. Despite decades of observations, one of Saturn's greatest magnetospheric puzzles still persists. Why does the planet's magnetic field not reveal its true rotation period? On Earth and Jupiter, radio modulation tied to the rotation of the magnetic dipole provides a direct measurement of planetary spin, but Saturn's magnetic field is too symmetrical, too aligned. There is almost no wobble, no tilt, no signature that allows scientists to mark a precise rotation rate. Instead, the magnetosphere itself seems to drift, shift, and evolve, influenced by plasma loading, ring interactions, and solar wind variability. This has led to the concept of dual rotational systems, the deep internal rotation of Saturn's, the slower, externally modulated rotation of the magnetosphere. The discrepancy between the two is one of the great remaining questions of Saturnian science. 7. The magnetosphere as Saturn's silent memory. If Saturn's interior theories describe the planet's heartbeat and its rings represent its symphony of ice, then the magnetosphere can be thought of as its memory field, a region that records every interaction, every solar wind pulse, every plasma injection from Enceladus, and every wave that vibrates through the field. In this magnetic environment, Saturn tells its silent story through plasma flows, through auroral rings, through SKR radio emissions, through oscillating field lines, through particles trapped, accelerated, and ejected. Every wave, every drift, every fluctuation is part of a narrative that stretches from the core to the rings and far into the void of the magnetotail. And as we move forward into Chapter 8, we will see how this magnetic architecture shapes and is shaped by the moons that orbit Saturn, creating one of the most interconnected planetary systems in the known universe. Chapter 8. The Rings as a Planetary Archive. As we move from the dynamic plasma environment surrounding Saturn, there is a natural step forward, one that draws us closer to the planet's most iconic and visually arresting feature. Saturn's rings, often seen as delicate ornaments suspended in the dark, are far more than fields of ice and dust. They are an archive, a geological and astrophysical record of events spanning hundreds of millions of years. To understand Saturn is to read the rings layer by layer, orbit by orbit, particle by particle. The rings are not static. They are living structures shaped by gravity, collisions, resonance, and sunlight. Through them, scientists gain access to a slow-moving chronicle, the history of debris, migration, catastrophes, and orbital evolution. In many ways, the rings function as a planetary fossil record, except the fossils move, spin, collide, and reconfigure themselves constantly under Saturn's gravitational rule. 1. Composition, a record in ice and shadow. Saturn's rings are composed primarily of water ice, clean, bright, and remarkably reflective. More than 90% of their mass is ice, with traces of silicates, organic compounds, and darker contaminants. This composition is a major clue. Whatever formed the rings was once rich in water, possibly resembling an icy moon or a mixture of comet-like material and primordial debris. The near purity of the ice suggests that contamination happens slowly. If the rings were billions of years old, micrometeorite dust would have darkened them significantly. Instead, their brilliance indicates youth, perhaps only 100 million years old. In cosmic terms, this makes the rings contemporaries of the dinosaurs, rather than remnants of the early solar system. Every ice particle carries chemical signatures in its surface layers. Under microscopes aboard Cassini, spectral readings revealed variations in water crystallinity, radiation exposure, and micrometeorite impacts. Some particles show signs of repeated resurfacing as collisions chip, shatter, and recalcify them into new shapes. Others carry soot, the darker thumbprints of infalling interplanetary dust. If Earth has sedimentary layers, Saturn's rings have spectral layers, chemical variations that reveal age, exposure, and origin. 2. Thickness and transparency. A thin book with millions of pages. Despite stretching hundreds of thousands of kilometers across, the rings are astonishingly thin. Most sections measure only 10-30 meters thick, thinner than a house, thinner than a small building. The result is a structure that behaves like both a fluid and a swarm. Billions of particles move in nearly perfect Keplerian orbits, each one a page in Saturn's extensive cosmic record. The rings exhibit subtle transparency when viewed backlit by the sunday. Certain regions, like the Cassini division, allow sunlight to pass through gaps between particles. This transparency provides clues about density waves, gravitational disturbances, and local particle sizes. Each semi-transparent band tells a different geological story, where moons have shaken the structure, where particles have clumped or dispersed, where debris has migrated inward or outward. 3. Collisions and cratering. Micro-bullet impacts in slow motion. Every second, microscopic dust grains from the outer solar system bombard Saturn's rings. These grains, moving several kilometers per second, strike ice particles and leave tiny craters or splashes of vaporized material. Cassini's Cosmic Dust Analyzer (CDA) detected the aftermath: ejecta clouds, chemical changes, and even particulate jets, where collisions expelled plumes of ice dust. These micro-impacts function like cosmic timestamps. 2 key insights arise. 1. Cratering frequency helps measure the age of the rings, much like crater studies on planetary surfaces. 2. The size distribution of fresh ejecta reveals ongoing processes such as aggregation, fragmentation, and vapor deposition. Through these impacts, the rings record everything that hits them, even the smallest interplanetary grains forged in distant regions of the solar system. 4. Orbital resonances, gravitational echoes, frozen in structure. The rings are sculpted by Saturn's moons, whose orbits create gravitational resonances, rhythmic tugs that carve patterns, waves, and sharp edges. One of the most impressive examples is the 2-to-1 resonance with the moon Mimas, responsible for the Cassini division. Every time a ring particle reaches a certain orbital position, Mimas delivers a tiny gravitational pull. Over thousands of years, these repeated tugs clear a vast gap. It is a gravitational dairy, a long-term record of Mimas's orbit and gravitational influence. Other moons generate spiral density waves and bending waves that resemble ripples in a pond. These waves propagate through the rings at measurable speeds, allowing scientists to reverse engineer their sources and reconstruct the history of moon migration. The rings act as seismographs, capturing gravitational oscillations that reveal moon positions and orbital evolution, internal oscillations within Saturn's core, sudden disturbances from impacts or tidal events. In this way, the rings are more than a structure, they are Saturn's gravitational memory. 5. Embedded moonlets, fossils still alive. Within the rings lie embedded moonlets, small bodies only a few kilometers wide that shepherd ring material around them. Some carve propeller-shaped wakes, while others gather dust into ephemeral clumps. These moonlets are remnants of past epochs, fragments of larger bodies that were shattered, or seeds of future moons slowly accreting material. Their existence indicates that the rings are part of a cycle. Moons break apart, fragments become rings, Rings spawn new moonlets. Moonlets merge into larger bodies. Saturn's ring system is not a static relic, but an evolutionary engine. 6. Meteoric events. Sudden inscriptions in the archive. Occasionally, larger meteoroids tens to hundreds of meters wide strike the rings. When they do, they leave temporary scars. Vertical plumes, dark smudges, or regions of disturbed orbits. These events behave like supernova remnants on a much smaller scale, expanding, fading, and blending into the background over several years. Cassini observed mysterious spokes in the rings, radial shadows that rotate with Saturn's magnetic field. These spokes are likely caused by micrometeorite impacts charging dust grains electrostatically, lifting them above the ring plane. They are temporary, unusual, and yet deeply revealing. The rings, once again, act as sensors of both impact events and electromagnetic conditions. 7. The rings as a chronological system. Taken together, the rings function as a chronological system, an ordered record of processes occurring over vastly different timescales. Minutes, collisions, vibrations, micro-impacts. Hours, spiral density waves, moonlit disturbances. Years, meteoroid scars, seasonal illumination changes. Centuries to millennia, resonant clearing, edge sharpening. Millions of years, moon migration, ring mass, evolution. Few objects in the solar system store information across such a wide temporal spectrum. The rings are as close as we have to a dynamic, self-updating geological record that can be read in real time. Chapter 9. The rings as a dynamic laboratory, collisions, feedback, and hidden systems. As we move deeper into Saturn's domain, beyond the acoustic signatures and the electromagnetic rhythms explored previously, the rings begin to reveal a far more complex identity. They are not merely passive bands of ice orbiting in mechanical obedience. They behave as a highly sensitive, constantly shifting laboratory, a place where gravity, light, plasma, and particle dynamics encounter one another in ways rarely seen elsewhere in the solar system. If previous chapters explored why Saturn's rings sing, this chapter asks a more intricate question. How do the rings respond, evolve, and reorganize themselves in real time, sometimes within hours, as forces act upon them? Saturn's rings behave like a system with memory. Every wave, every collision, every electromagnetic ripple leaves a trace, an imprint that reshapes the next sequence of interactions. To understand this, we need to examine the rings not simply as material belts, but as a responsive feedback system built from billions of icy particles that behave collectively like one immense, self-regulating structure. 1. A sea of particles in constant collision. To grasp the complexity of Saturn's rings, one must first acknowledge the sheer scale of activity occurring at every second. The rings consist of countless particles ranging from micron-sized frost grains to boulders several meters wide. Each revolves around Saturn at a slightly different speed, creating an environment where collisions are inevitable. But unlike collisions on Earth, governed by friction and energy loss, ring collisions occur in a near vacuum and are surprisingly gentle. These impacts rarely shatter particles. Instead, they redistribute angular momentum, smoothing sharp edges, equalizing orbital velocities, and maintaining the incredibly thin geometry of the rings, sometimes as thin as 10-30 meters across a radius of 140,000 kilometers. This delicate balance creates an emergent behavior. Density waves propagate like ripples in a pond, Clumps form and dissolve in mere minutes. Entire regions oscillate in brightness as particles rearrange. It is a fluid made of solid ice, one of the solar system's strangest paradoxes. 2. Spiral density waves, the rings that ripple like galaxies. From a distance, the rings appear static, but up close, spacecraft have observed the unmistakable signatures of spiral density waves, patterns similar to the arms of galaxies. These waves are triggered primarily by Saturn's moons through orbital resonances. Imagine a moon such as Mimas completing one orbit in the same time that a ring particle completes exactly two. Each time they align, the moon's gravitational pull tugs on the ring particle at the same orbital phase, just like pushing a swing at the perfect moment. The result is amplification. Tiny gravitational nudges accumulate until ring particles begin to cluster into spiral patterns that stretch for tens of thousands of kilometers. Although these waves look like they are made of static icy arcs, they are actually moving, propagating outward through the rings at speeds measurable in meters per second. Saturn's rings, then, are not a frozen sculpture. They are an ocean responding to distant moons with rhythmic precision, encoding their orbital interactions into luminous ripples. 3. Vertical waves, when the rings rise and fall like a breathing sheet. Not all waves move sideways. Saturn's rings can rise vertically, swaying above and below their usual plane in graceful, oscillating sheets. Vertical waves form when a moon's gravitational influence pulls ring particles slightly out of alignment, tilting them up and down much like vibrations on a drumhead. Cassini revealed dramatic examples near the equinox of 2009, when the sun's low angle cast shadows tens of kilometers long across the rings. What seemed flat suddenly revealed itself as corrugated terrain, mountains and valleys in miniature. These waves offer insight into the mass distribution within the rings, the stiffness of the particle ensemble, and the long-term evolution of ring thickness. Vertical modes also interact with Saturn's magnetic field, producing subtle electromagnetic distortions that feed into the ring songs captured by Cassini's instruments. 4. Self-gravity wakes. The rings organize themselves. One of the most compelling discoveries is that ring particles don't merely respond to external influences. They self-organize into intricate structures called self-gravity wakes. These are elongated clumps, like tiny gravitational flocks that stretch and break, repeating endlessly. The cycles occur because ring particles are massive enough to attract one another, but the shear of orbital motion constantly shears them apart. The result resembles a pattern of alternating dense and sparse regions, behaving similarly to turbulent airflow, yet shaped by microgravity and orbital mechanics rather than wind. Self-gravity wakes are responsible for much of the textured brightness observers see in high-resolution ring photographs. They also influence how light scatters through the rings, subtly altering their color and luminosity. In essence, Saturn's rings are a self-adjusting network capable of forming and dissolving structures without any external forcing at all. 5. Meteoroid bombardment, invisible rain that repaints the rings. Every day, microscopic meteoroids collide with the rings. Most are no larger than grains of sand, yet their combined contribution is significant over geologic time. These impacts darken the rings with foreign material, generate clouds of ejecta, spread dust into neighboring zones, and inject new chemical signatures into the icy particles. Cassini's data indicates that meteoroid bombardment is one of the key forces slowly aging the rings. The pristine whiteness of the ice is gradually contaminated by carbon-rich dust, an effect that may help determine the ring's true age. Every impact also produces local disturbances, momentarily pushing particles away before they settle back into equilibrium. In other words, the rings experience a ceaseless, invisible rainfall that subtly modifies their structure. 6. Saturn's magnetosphere, a sculptor working in the dark. Saturn's magnetic field interacts constantly with its rings, especially with the smallest particles, those below a few microns in diameter. Charged grains respond strongly to electromagnetic forces, which can trap particles, accelerate them outward, or eject them entirely from the rings. This selective filtration means the rings evolve not only through gravity, but also through electrodynamics, a feature almost unique among planetary ring systems. The B ring, for instance, includes regions where charged grains levitate slightly above the ring plane, creating microlayers detectable only through radio occultation. Saturn's magnetosphere, then, is sculpting the rings even when nothing visible seems to be happening. 7. The feedback system, rings, moons, field, and planet as one. Saturn's rings do not operate in isolation. They exist in a chain of feedback loops. Moons shape rings through resonances. Rings push back on moons through gravitational torque. Magnetic fields influence the smallest particles. Plasma from the rings feeds Saturn's magnetosphere. These relationships mean the rings are not a decorative accessory, they are an active component of Saturn's larger system architecture. Small changes propagate through the network. A shift in a moon's orbit can trigger new wave patterns. Variations in solar wind can alter particle charging. Seasonal lighting can reveal or suppress vertical features. The rings become a giant sensor, recording the environmental state of Saturn's realm. 8. The rings as a time capsule of system evolution. Because the rings respond so sensitively, scientists can read them like a geological record. Wave patterns trace historical orbits of moons. Dust contamination indicates meteoroid flux over time. Vertical disturbances correlate with past collisions. Surface brightness variations reveal seasonal change. The rings are a dynamic archive not just of Saturn's present, but of its past. Every oscillation, every collision, every grain of dust tells a story spanning millions of years. 9. Toward Chapter 10, the fate of the rings. As we conclude this chapter, one question emerges from all this complexity. If the rings behave like a dynamic, evolving system, what will ultimately happen to them? Will they fade into diffuse mist, collapse inward, and rain onto Saturn, or stabilize into a long-term architectural feature of the planet? To answer that, we must dive into the physics of ring decay, mass loss, and the phenomenon now called ring rain. This leads us naturally into the final part of the documentary, Chapter 10, Saturn, Time, and the Future of the Rings. 1. The rings are falling literally. One of the most astonishing discoveries from the Cassini mission came in 2018, when scientists confirmed that Saturn's rings are slowly raining into the planet. This phenomenon, called ring rain, occurs when charged particles from the magnetosphere interact with the icy grains of the rings. UV radiation from the sun charges the particles. Magnetic fields pull them along invisible arcs, and they spiral into Saturn's upper atmosphere. Hydrogen molecules in the atmosphere collide with these grains, stripping away water and breaking them down into vapor. The rate is measurable. As much as 10,000 kilograms of ring material falls into Saturn every second. At this pace, the rings may disappear in 100 to 300 million years, a short time on cosmic scales. This means the rings are not ancient leftovers from the birth of the solar system. They are young, temporary, and slowly fading. 2. The mystery of their age. Before Cassini, scientists debated whether the rings were billions of years old or only a few 100 million. Cassini's high-precision measurements of dust, ice mass, and contamination shifted the balance sharply. The rings are too clean. If they were billions of years old, they should contain far more dust, micrometeorite debris from the constant bombardment of space. But instead, the rings appear extraordinarily pure, 94% water ice, only a trace of darker material. This led scientists to propose a much younger age, possibly coinciding with dramatic events. A moon torn apart by Saturn's gravity, a collision between ancient icy bodies, a late-forming ring system long after Saturn itself formed. Thus, the rings may be a temporary feature in Saturn's long life, a momentary brilliance in an otherwise quiet planetary history. 3. The rings redistribute momentum. Saturn's rings are not passive. They dynamically exchange momentum with the planet and its moons. This continuous interaction affects the planet's rotation and the orbits of its moons. The rings exert torque through processes like a. Ring-moon resonance. Moons such as Mimas, Enceladus, and Dione pull on ring particles via gravitational resonances. These resonances carve out gaps, the Cassini division being the most famous, and can accelerate particles inward or outward. B. Angular momentum transfer. The rings absorb and release angular momentum over millions of years. Some moons move outward due to this transfer. Some ring material moves inward and falls into the planet. This means Saturn's rings actively sculpt the architecture of the Saturnian system, redistributing momentum like a vast cosmic gearbox. 4. Saturn's rotation revealed by the rings. One of Cassini's late surprises was that scientists could determine Saturn's internal rotation by reading oscillations within the rings. The planet vibrates very subtly due to internal pressure waves, convection currents, and interactions between its deep layers. These vibrations create tiny periodic variations in Saturn's gravitational field. The rings respond like a seismograph. Each oscillation imprints a pattern: densely packed waves, spiral arcs, and narrow resonances detectable in the B ring. By studying these gravitational ripples, scientists determined Saturn's deep rotation is 10 hours, 33 minutes, 38 seconds. This rotation period was previously unknown because Saturn has no solid surface. In this way, the rings are not just decoration, they are diagnostic tools for reading the physics of the planet itself. 5. The plasma connection revisited. In Chapter 9, we explored how Saturn's rings interact with the magnetosphere, influencing plasma flows that sweep through the system. In Chapter 10, those processes take on an added depth. The rings change Saturn's plasma environment in return. Tiny grains of ice become charged by UV radiation and plasma bombardment, and then are accelerated, ejected, ground into even finer dust, or spiraled inward due to electromagnetic drag down. This plasma erosion contributes to ring rain, affecting atmospheric chemistry as particles fall into Saturn's ionosphere. Cassini discovered that ring rain leaves chemical fingerprints, water vapor, hydrocarbons, compounds that should not exist naturally in Saturn's upper atmosphere. Thus, the rings act like atmospheric delivery systems, feeding Saturn materials from space. 6. What happens when the rings are gone? A future Saturn without rings would look dramatically different. A. Changes in atmospheric heating. Today, ring shadows create bands of cooler and warmer regions in Saturn's upper atmosphere. Removing the rings alters this energy balance. B. Orbital adjustments. Some moons depend on ring interactions to maintain their current orbits without the rings. Resonances shift, orbital distances adjust, tidal heating patterns change. This could influence volcanic activity on moons like Enceladus. C. Visual identity. Saturn would resemble Jupiter, more closely striped, stormy, and cloud-dominated. If humans ever observe this far future Saturn, it will seem almost unfamiliar. 7. Could the rings reform? Yes, Saturn's rings could return. In the distant future, catastrophic collisions between moons or large comets could again generate the debris needed to form a ring system. In this way, Saturn may go through multiple cycles: ring formation, ring decay, ring loss, ring rebirth. The planet's iconic rings might be a recurring phase, not a permanent trait. 8. Saturn's rings as a window into planetary evolution. When scientists study Saturn's rings, they are not just learning about one planet, they are uncovering universal planetary behaviors: how moons evolve, how debris disks form, how angular momentum shapes planetary systems, how collisions sculpt worlds, how plasma and gravity interact. Saturn is a natural laboratory, a scaled-down model of the disks that formed the solar system itself. Understanding its rings gives clues to how Earth, Jupiter, and even exoplanetary systems came into being. 9. The final perspective. Saturn's rings, in the grand timeline of the solar system, are like a fleeting flare of beauty present long enough to inspire human wonder, but brief in cosmic terms. They are dynamic, complicated, and constantly changing, a choreography of ice, light, and gravity played out in silence. When we look at Saturn today, we witness a unique moment in its history, a moment when debris, shattered ice, and cosmic dust unite to create one of the most striking structures in the universe. Future generations may see a dimmer Saturn. Far future civilizations may see a ringless world. Another era may witness rings reborn from chaos. But for now, in this epoch, Saturn sings in the dark, and its rings are the song.